once again, we are back with another exciting session, and I, Ajay Jha, on behalf of ACS India team, welcome you to today's ACS Science Talk session. And just to update you on the upcoming ACS Science Talk, please visit our ACS India webpage that you can see on your screen and register for the upcoming sessions on 14th May and 28th May. We have also updated the past lecture recordings in the ACS Science Talk virtual library section. Please visit, like, subscribe, and share among the scientific community. To keep you updated with the upcoming scientific cutting edge science and upcoming latest events, product launches at ACS, we have this ACS monthly newsletter, ACS Insights India. Subscribe today for free. We'll provide the link into the chat box later. To begin with the scientific session, it's an honor and pleasure to have Professor Gerald Meyer with us. Professor Meyer earned his BS in chemistry from State University of New York at Albany in 1985 and his PhD in chemistry from the University of Wisconsin at Madison in 1989 with Professor Arthur B. Ellis. He was appointed a postdoctoral associate at the University of North Carolina at Chapel Hill with Thomas J. Meyer and began his independent research career at Johns Hopkins University in 1991. Professor Meyer was Bernard N. Baker Professor of Chemistry from 2009 to 2013 and Chairman of Chemistry at Johns Hopkins University from 2011 to 2013. Since January 2014, he has held the position of Professor in Chemistry and is also the Deputy Director of DOE Energy Frontier Research Center on Solar Fuels at the University of North Carolina at Chapel Hill. He has served on the editorial advisory boards of Langmuir, Inorganic Chemistry, Chemistry of Materials, and Journal of Physical Chemistry, and as Associate Editor of ACS Applied Materials and Interface since 2012. Professor Meyer has authored or co-authored over 200 peer-reviewed articles in fundamental and applied research areas with a primary focus on material science, inorganic or coordination compounds, and extended solids, and is co-inventor in 3 patents or disclosure.
Yeah, so thank you very much, Diksha. It's my pleasure to tell you, to start with a little bit about ACS Applied Energy Materials, which is a new interdisciplinary journal that focuses on energy storage and energy conversion. And it's been my privilege to be the deputy and founding editor of this journal. And it's the first ACS journal that's focused specifically on energy applications. And our goal is to disseminate key advances in energy sciences that impact applications in energy. We're very much focused on the applications of new materials. And these include, but are not limited to, batteries, supercapacitors, photovoltaics, and materials for catalysis. And the interfaces between in electrodes, very often membranes. Our journal has been growing rapidly. We get a number of nice submissions from all over the world, including India. And we're hoping to see our journal grow into new and other areas. So that's a little bit of background on ACS Applied Energy Materials. And I encourage you to submit your best work. We really have the focus on applications. But if you, for example, have synthesized some new materials that you believe have an application but haven't yet had a chance to test for it, those types of submissions are welcome in our journal. We simply ask that you provide some context in writing your paper as to where you anticipate those applications will be. In other words, if you take a look at the state of the art, what do these materials offer that doesn't already exist in the field? And how can we take this to the next step? So those types of papers we sometimes call synthesis and characterization. And we're certainly interested in those submissions. Just provide some context as to where you think that will impact energy. And the impact of your paper, we believe, will be much stronger. So that's a little overview of our journal. I also wanted to share with you today a little bit about my own area of research, which has applications, as I'll tell you about, in dye-sensitized electron transfer. And the research, the fundamental research I'll be telling you about, has been funded by the US Department of Energy, and most recently in a solar hub that we call CHASE, which is specifically focused on generating liquid fuels using sunlight as the only energy input, and the small molecules you find in air as the only chemical feedstock. But before I get there, let me just give you a little history of dye-sensitization. Point out that it's a very old field. In fact, if you look back in the photographic field with latent image formation in silver crystals or silver halide materials, you can track dye-sensitization back into the 1800s. So it's a very, very old area of science. But in the 1960s, scientists, mainly in Germany, began putting molecules or dye molecules on flat semiconductor surfaces. And they were interested in the fundamental aspects of electron transfer reactions at these dye interfaces. There was no pretense in their work of a practical application. And the reason for that is that a monolayer of dyes on a flat surface simply doesn't absorb that much light. If you were to take a monolayer of a phthalocyanine dye that you find in blue jeans, which are some of the strongest light absorbers, highest extinction coefficient dyes that I know of, and put it on a piece of window glass, and then held that up to your eye and looked through it, your eye could just barely see it. Most of the light transmits through. So for molecular approaches to solar energy conversion, molecules on flat surfaces just don't work very well. The efficiencies are very, very low. So the next idea, kind of historically, was to say, well, let's make a very thick layer of dyes. If I can get a longer path length and get the Beer-Lambert law on my side, I can harvest more light energy. And that certainly works. You can make materials that are very opaque, and there are many examples in the literature. But in terms of energy conversion, it hasn't so far been a winning strategy. And at least two challenges have been identified, which people are still trying to overcome. One of which is that you can create an excited state, say right here in the middle of this layer of film, and it doesn't get to the interface in order to transfer an electron into the semiconductor, a process we often call charge separation. Said differently, the exciton diffusion length of that excited state is shorter than the penetration depth of the light into the film, so you don't successfully convert light to electrical energy conversion. The dye simply relaxes through radiative and non-radiative means. The other challenge has been that if the dye does get to the semiconductor interface to separate charge, then once it injects an electron, you create an oxidized dye in an environment where the oxidized dye is not well stabilized. It's typically a very low dielectric environment, and those are conditions that can promote very rapid back electron transfer. So, well, there are people, particularly in the organic photovoltaic field, that are still working on this type of approach, particularly when you want to harvest all of sunlight. It's very, very challenging. Well, it was in 1991 that Michael Gretzel and Brian O'Regan in Switzerland came up with a very novel idea. And that was, let's get rid of these planar electrode surfaces, single crystals or thin films, and instead use a very high surface area film. And initially these were just called colloidal films because the idea was to take colloidal nanoparticles and cast them in a film. Now we call them mesoporous nanocrystalline to really emphasize the importance of the mesoporosity. But these materials, which are generally made from anatase TiO2, although other wide bandgap semiconductors work, have tremendous surface areas. So when you attach a monolayer of dyes to these, the materials become opaque. And when you do that experiment of holding them up to the sunlight, your eye can't see through them. You effectively absorb all of the incident light, depending on the color of your dye. So the light harvesting problem is solved. And in addition, when an individual dye injects an electron, that oxidized dye now is in an electrolyte. You can submerge the whole film in an electrolyte solution with salt that stabilize it and prevent those unwanted recombination reactions. And since 1991, the field is advanced. It's now possible to buy from several manufacturers the dyes, the mesoporous thin films, and very quickly you can get into an efficiency range that's 5 to 6%. There are record efficiencies that have been confirmed at the National Renewable Energy Lab that are in excess of 11%. That's more challenging. And really to be competitive for applications, for widespread application, we need to get up to about the 15% efficiency range. So far, the dye-sensitized solar cells have mainly niche type applications. Now, how do they work? Well, the models that were developed in Germany are the same ones that are used to explain how energy conversion works in these mesoporous films. And in particular, I would point out the work of Heinz Gerischer, who to many is sort of the father of photoelectrochemistry. He applied the electron transfer kinetic models to interfaces, and his theories have withstood the test of time. But very simply here, starting on the left-hand side, the band gap of anatase TiO2 is about 3.2 electron volts, and that corresponds to photon energies in the ultraviolet region. About 2% of sunlight is absorbed by anatase TiO2, so it's a very small fraction, and it's not a useful material then for solar harvesting. But if you attach a dye molecule to the surface, you can excite that dye with visible light. And if it's a strong enough photoreductant in its excited state, it can inject an electron into the conduction band, and that can give rise to a photocurrent and power generation. Because the dye is absorbing light at longer wavelengths than the semiconductor, we often say it sensitized the semiconductor to longer wavelengths of light, and therefore dye and sensitizers, those terms can become synonymous. We sometimes just call the dyes sensitizers. Now, once you transfer an electron into the semiconductor, you create an oxidized dye. And in a regenerative solar cell, a redox mediator, it's typically iodide, regenerates that ground state dye so that the sensitizer can absorb another photon and inject it. We call these regenerative solar cells because even though you're oxidizing iodide at this photoelectrode, once the electrons run through an external circuit and do useful work, they return to a platinum counterelectrode where they reduce D+ back to D0. So therefore, all the oxidation chemistry that occurs at the dye-sensitized electrode gets reversed at a counterelectrode, and there's no net chemistry. You simply convert light to electrical power. And one thing I will come back to is that when Gerischer looked at these kind of pictures in more precise detail, he really emphasized distributions. and the overlap of the sensitizer with the unfilled states in a TiO2, for example. And he also showed that these states are not fixed and can change based on the environment. And for a single crystal material like TiO2, the band edges can move in 59 millivolts per pH unit when put in aqueous solution. So they move around and they care. In acetonitrile solutions, the presence of Lewis acidic ions like lithium can have a big effect on those. And one of the challenges of the field is that we often don't know where those acceptor states or conduction band states are in energy. The methods that Gerischer used to determine them at single crystal surfaces are often not applicable to very small nanometer sized particles. So this is a challenge to understand this overlap. And I'll show you a little bit of that later in my talk. Now, when I moved from Johns Hopkins to North Carolina, I became very interested in another type of dye-sensitized solar cell that we call a photoelectrosynthetic cell. So rather than just converting light to electrical power, we're going to try to convert light into some fuels that can be stored and used. And one example of that is shown here, where at one electrode, rather than oxidizing iodide, we're going to convert water to dioxygen, water oxidation reaction. And that's much more challenging than oxidizing something like iodide. And in general, the sensitizer or dye itself, although it can be thermodynamically capable of driving the reaction, kinetically can't do it fast enough because the electrons that are injected will recombine too quickly. So we use what we call chromophore catalysts, where there's a light absorbing dye shown as this blue sphere, and then these Pac-Man type creatures are the molecular catalysts. And I'll show you a specific example of that later in my talk. But we need then to have 4 interfacial charge transfer events before we can make the oxygen-oxygen double bond. And in fact, not only in dye-sensitized electrosynthetic cells, but in general, the water oxidation reaction is a bottleneck in many energy conversion schemes. If you want to split water into hydrogen and oxygen gases, the hard part is the water oxidation. Proton reduction is a much more facile reaction. We here at our previous EFRCs and now at Chase are interested in, instead of making hydrogen gas, reducing carbon dioxide at an electrode. And we've imagined using 2 different dye-sensitized electrodes. One would be a P-type material. We always need to use these high surface area films because we're relying in our EFRC work on dyes to absorb the light. But could we use the electrons and protons that we get from water oxidation to reduce CO2 to a useful fuel? And in our EFRC research, we were successful in getting C1 products like carbon monoxide to electron transfer reactions. And now we'd like to extend that to getting things like methanol, a 4-electron transfer product, or carbon-carbon bonded products like ethanol. I should say that the overall efficiencies of these dye-synthesized cells are still not high. If you use sunlight as your source, the efficiencies are getting close to 1%, but they're still very low. And there's also issues of long-term stability that represent challenges for our field. The Faradaic efficiencies, based on how many photons are absorbed and how much fuel we make, can be very high. So that part's encouraging. So I'm going to give a little overview today. I'm going to try not to get into too many details of specific aspects of the research that we find to be very interesting, and frankly, that we have funding to pursue. And the first part of my talk, I'm going to overview what we call halide photoredox chemistry. And as I mentioned, iodide is a spectacular electron donor for regenerative dye-sensitized solar cells. And we were initially interested in why it works so well when other outer sphere redox mediators like ferrocene, ferrocinium don't work so well. And that led us into some very interesting chemistry. One of the unique aspects of halogen redox chemistry is that it's often coupled to bond forming and bond breaking steps. So when you make an iodine atom, for example, it reacts, and you can monitor those subsequent reactions, and making chemical bonds with sunlight is of fundamental interest. So we'd like to understand the redox mechanisms and bond formation reactions. We're also interested in using halogens as redox mediators. Could we, for example, create electrodes where we use dye-sensitization in seawater or in brine to selectively oxidize chloride? And those are challenges that our field would really like to pursue. The second part of my talk, I'm going to switch to giving you a little overview about the electric fields at these interfaces. And these electric fields are very different than what some of you may be familiar with bulk semiconductor materials, where you can generate a Schottky junction and large electric fields in the interface. For the intrinsic semiconductors that we studied, those types of Schottky junction models have proven not to be useful for understanding energy conversion. But rather, the electric fields generated by ions or the injected electrons can have a large impact. And we're studying those and monitoring the fields and how they impact migration of ions at the interface, the orientation of the dyes, and what it's telling us about the structure of the solvent and the electric double layer right around the semiconductor nanoparticles. And then finally, in the third part of my talk, I'm going to shift over to interfacial electron transfer reactions that involve having a sensitizer inject an electron and then having a covalently bonded electron donor, like in the chromophore catalyst assemblies. And what happens to the linker when it can promote electronic coupling between these two. And one of the important messages from this is that we believe dye-sensitization can be a way of probing and testing the theories of Heinz Gerischer and Rudy Marcus and others. And these potential energy surfaces are actually what Marcus predicted some time ago would happen when the electronic coupling HAB between a sensitizer and donor is increased by having a linker that promotes that kind of coupling. So let me start back with halide photoredox chemistry. I want to really introduce the people who started us in this chemistry. And this was started by Ludo, who was a postdoc here and has now returned to Belgium. And Ludo wanted to try to create a very high concentration of halides at the interfaces. And he was aware of these hydrogen bonding motifs. And it turns out that these are very good receptors for halides. So especially if you're in a non-polar solvent like dichloromethane, he could show by NMR that these halides would interact here in this pocket and make strong adducts. And he did this in fluid solution. There was no interface. The strategy was, let's study at first the molecules in solution, and then we'll translate what we know to interfaces. But you can see there are very large equilibrium constants for binding. These molecules and many of the dyes used in dye-sensitized solar cells luminesce. So if you excite them with light, you can see intense photoluminescence. And what Ludo found was that when he binds the halide here, it actually enhances the luminescence. And once there's one equivalent here, as he goes to higher concentrations, he could see the luminescence quench. And the excited state lifetime did that as well. So that was curious to us, and it made us wonder why. And what we found was that when you put a chloride or an iodide in this pocket, it stabilizes it. A lot of this equilibrium constant is due to stabilization of the ion, and it becomes very hard to oxidize that. So it's an important lesson. If we can take molecules or interfaces and put them in seawater and selectively bring the chloride in and bind it there, suddenly that chloride becomes a lot harder to oxidize than all the other chloride ions that are diffusing around in solution. So how do we oxidize just that one? And that's a challenge for us. But using theoretical approaches and density functional theory, Ludo went through and assigned partial charges to all the atoms in the molecule and worked out the so-called work terms in the Rem-Weller expression. And what I can tell you for sure is that the theory predicts exactly where the halide binds. The first halide went here, and in some cases he could see the second halide go here when there was one sitting. And he could confirm that by NMR. But the stabilization he measured was very similar to the equilibrium constants, but not quite the same. And we feel we need a larger database to really test whether the theoretical predictions are in line with experiment. Wes Swords, who's a graduate student, was a graduate student, he's now a postdoc with Taeshik Yoon in Madison, Wisconsin, said, why don't we use electrostatics to help bring dyes to interfaces, and was very successful in doing that. He made this ligand we call TMAM, and you can see it as these two cationic amines that will electrostatically bind halides. And what he found was that it really likes to interact right here at this interface. These are the resonances of the 3,3' hydrogen atoms. And when he titrates in halide, he can see a large shift in them. And also interactions, I'm sorry, these are the interactions with the methylene carbons on the TMAM ligand, these hydrogens here. And this shift in A is what happens to the 3,3' hydrogens. So it formed a little pocket there. And by tuning the energetics with iodide, he could see direct electron transfer at these interfaces. And he did successfully apply it to interfaces to show that this could promote energy conversion. We now have a team of people working on these kind of applications. We've learned a lot. Michael Turlington, who just graduated and is starting a postdoc with Kirk Shans in Texas, found that if he had a halide just hydrogen bonded here, in some cases he could photorelease that halide. It wasn't exactly behavior we were looking for, but it was interesting to us, and he pursued that. Sarah and now Aaron were looking at cases that were more similar to Wes's, where we could get two halides very close to each other. And we're wondering, could it be possible to have electron transfer and I bond formation occur very rapidly, or perhaps even in one concerted step? And then Xander Dietz has been looking at iridium complexes where he can, again, use these tertiary methylamines to bind a halide here and estimate the redox potential. So a little bit more fundamental science. A nice aspect of these iridium complexes is that they are able to oxidize chloride quite efficiently, although they don't harvest as much sunlight as the ruthenium compounds do. I'll turn now to interfacial electron transfer and the electric fields. And this is work that Shane Ardo started when he was a graduate student. He's now in the faculty at UC Irvine. And this is another way to think about dye sensitization. And that is that each dye molecule undergoes a series of charge transfer reactions. Light absorption forms the metal to ligand charge transfer excited state, and then excited state injection occurs, and then regeneration through halide oxidation. And if you look at the state-of-the-art dye-sensitized solar cells, you can compute that each dye does that whole cycle in about 200 nanoseconds. Unfortunately, sunlight is very diffuse. The good thing is we have a lot of solar photons. But what that translates to meaning is that once a photon is absorbed, the sensitizer runs through this cycle, and then it sits back in the ground state and it waits for another solar photon. And it does it about twice per second. At the short circuit condition, you try to pull those electrons out as quickly as you can. At open circuit, you just build up as many electrons. You move the quasi-Fermi level of the TiO2 up toward the vacuum level to generate a large photovoltage. But at the power point, where the product of current and voltage is a maximum, that's where you want the highest energy conversion. And what Shane found, and others as well using the charge extraction technique, is that at the power point in a 20 nanometer TiO2 particle, there are about 50 electrons roughly that are residing in there. And roughly on a 20 nanometer particle, there are about 500 dye molecules, just to give you a little idea of the stoichiometry. And for a long time, people thought that those electrons didn't do anything. They didn't have an impact. They didn't generate an electric field because of the dielectric constant of the electrolyte, the permittivity of the TiO2. It just screened the field. And Shane, over 10 years ago now, showed that that wasn't the case. And he was doing regeneration studies. This is some transient absorption kinetics. But he expected at these delayed times to see the injected electron and the oxidized iodide. And instead, he got this first derivative looking spectrum. And actually, when he first discovered it, it was a very, very small effect. And then he found some dyes that he could kind of optimize the effect for. So it was very careful work on Shane's part that allowed this discovery. And he was able to show that it's due to an electric field. And it's very similar to the types of electric fields you can see in Stark spectroscopy, but in a Stark experiment, and I'll show you some data for that, the electric field is fixed with respect to the laboratory frame of reference, and dye molecules are frozen in a glass. It could be a dye-sensitized film, but some are parallel, some anti-parallel, and some orthogonal to the field. And it impacts their absorption spectrum differently. So in Stark spectroscopy, you typically report the absorption spectrum with the electric field on and with it off. And when you take the difference, you get this second derivative looking feature, where what Shane was seeing was a unidirectional shift. And that's because the field is essentially constant with respect to the orientation of the dye. And if you measure this change, and you know the dipole moment change of your dye molecule, you can calculate the electric field through this simple expression. And surprising, I think, to the dye-sensitized field, it was huge. It was a much larger field than anyone expected. And if you ask the question, well, what is the dye molecule feeling right at the ruthenium center? It's about 40 millivolts of field that's dropping across the semiconductor electrolyte interface. So we've been interested in that for a long time since. I'll just give you a couple of interesting examples. This is the work of Renato Sampaio, who's now at Brookhaven Labs. Renato came to Johns Hopkins on the Science Without Borders program from Brazil. He's an outstanding scientist. Quentin Logue is a new graduate student who's getting involved in this research. And without going through all the details, if the field is parallel or anti-parallel to the orientation of the dipole of the dye, we get a blue shift or a red shift. So it's kind of a sore thumb in our experiments. And when he bound this ruthenium pentamine dye through carboxylic acids, he could see right in the ground state spectrum a shift that reported on the electric field. When he made the ester version of the dye, what he found was that the magnitude of the field and the Stark signature, as we often call it, changed sign. And what was happening was the molecules were actually flipping over. And it was remarkable to me that they were doing it, and also that we could tell. And what Renato and now Quentin have been showing is that when the molecules flip over and they're standing on their heads through the amine, the electrons recombine more quickly. There's stronger electronic coupling that way. And that's what this blue trace is shown here. Once they recombine, you get a metastable state though, and it takes time for the molecules to flip back down to their thermodynamic state. And that's what this red spectrum is shown. And there's actually a deuterium isotope effect for that. And we're wondering if we use different binding groups here that don't bind too strongly, can we use those as a probe to know when the field shifts over? There are many applications that use electric fields to pull molecules and orient them. But at these dye-sensitized interfaces, it's a new observation. Jenny Schneider, a former postdoc who's now at the University of Munich in Germany, and Rachel Bangle, who just defended her thesis but will be moving as a postdoc to Duke, have been wondering about the field right at the semiconductor oxide interface. And they've been using Gerischer theory to analyze it. And I don't have time to go through it all, but they've been using, instead of TiO2, transparent conductive oxides, like ITO. TCOs are generally called, but they have behavior that's more like a metal than a semiconductor. And what that allows us to do is tune the Fermi energy of the conductor with respect to the dye molecule. And we can probe the interfacial kinetics for electron transfer through all of Gerischer's curve. And what they did was fix dye molecules at different positions within the electric double layer. And it turns out that the reorganization energy for electron transfer, which is a measure of the barrier for transfer, is directly related to the formal potential. So by measuring this whole distribution, they can extract the reorganization energy. And what they found was when they were very, very close to the surface, the reorganization energy was very small, much smaller than what we expected for dielectric continuum theory. And then when they moved the dyes further from the surface, they started getting reorganization energies that you'd expect from measurements in bulk solution. But why we're excited about that is it says that if we can do catalysis or photoinduced electron redox reactions very close to the interface, the barriers that we normally encounter from the solvent stabilizing all this charge will be absent. And we have an opportunity then to drive reactions more efficiently. And I have to say it's a big departure for us, because when we started in our EFRC research, we always wanted to do catalysis as far from the interface as possible to try to prevent those back reactions. And now we're seeing that there's a real kinetic advantage to running the reactions closer to the surface. I'll point out also, this is more fundamental, that in a lot of these studies, we want to know what the change in dipole moment is. So we went to the trouble of setting up a standard Stark apparatus, which is a very old area of spectroscopy. It's basically a UV vis spectrometer with a cryostat that allows us to potentiostat a thin film and vary the electric field. And Andrew Meyer, who was a graduate student who just started a postdoc with Maria Abramson in Sweden, did set this up and measured sort of the classic dye sensitizers that we like, these metal to ligand charge transfer complexes. And lo and behold, there were some big surprises. One of which was in the ground state absorption of these molecules, at long wavelengths, there's very little absorption for iron and ruthenium, but for osmium, there's a very intense band, and that's due to a singlet to triplet charge transfer absorption, or it's been assigned that way. The bottom line is that in stark spectra, they're much more pronounced, and we're now trying to figure out why. So I'm a little long-winded here. I'll switch over to this story a little more quickly. This was an idea of moving the oxidized sensitizer away by intramolecular electron transfer. And here at UNC, our solar hub has a whole bunch of catalysts and many, many different dye molecules and ways of integrating them to semiconductors. And the question is, what's the best linkage? How much coupling do we want between the dye and the sensitizer? We know what we want. We want to get all the oxidizing equivalents if we're driving water oxidation, or all the reducing equivalents if we're reducing CO2 out to the catalyst. But how much coupling is best? And you'd think that might be something that's known, but it's really not. Is an ester link better than an ether? We don't really know that. And Kahu, who's now on the faculty at Fudan University, looked specifically at this type of a catalyst, where you can see there's two sp3 hybridized carbons between a sensitizer and this water oxidation catalyst. Phil Castellano, who back in regenerative solar cells days looked, he's now on the faculty at NC State, looked at a single methylene carbon and whole transfer out to this. And we found in this case that there was a real advantage to moving the oxidizing equivalent out here. You could generate a larger open circuit voltage, get more Gibbs free energy from the solar cells. In both those cases, it was hard for us to understand because we had a flexible spacer where those donors were. And we became aware of this work of Kiyoshi Robeson and Curtis Burlingett in Canada, where they had a more rigid type spacer, an aromatic spacer between the two. And what we found in their studies was that the nature of that bridge, that aromatic bridge, whether the thiophene could become coplanar with the phenyl or whether it was at a right angle, had a big impact on the recombination electron reaction. And that was a little surprising to us. We didn't expect that these electrons would see a bridge molecule so far away, but they do. And there's a pathway by which the electrons would come back, in this case, to these oxidized triphenylamines. Eric Pachota, who was a graduate student here, went and studied the reactions, and I have been a little long-winded, so I'm going to quit here, but what he found was that the Marcus Gerischer theory, if you will, predicts that as you increase the coupling by having a more conjugated bridge as opposed to one that's orthogonal, you do change the Gibbs free energy. The minimum of these curves change. But the intersection point, the barrier, did not change very much. And using an I-ring analysis, he saw that there was this compensation between the entropy of activation and the enthalpies. So the barrier was pretty much the same, but the coupling was certainly changing the overall Gibbs free energy change. So with that, I would just conclude and say, I think dye sensitization really provides an opportunity, if you're interested in molecules, to have practical applications. They haven't been realized in a large way, but there are niche applications of dye-sensitized solar cells. and for dye-sensitized water oxidation or halides HX splitting, there's opportunities there. I think equally important is that because you can photoinitiate one electron transfer reactions, there's an opportunity to understand fundamentals and test existing theories. And one of the examples I showed you of that was for electric fields at interfaces, where we can get strong coupling and weak coupling depending on the orientation of a bridge. And I'll just end with a real nice quote that I like from an artist who's passed away here in the United States, Georgia O'Keeffe. And Georgia, in her realism period, had these very nice quotes where I think they apply to experimental science, where the details that we first learn when we go into a new field are often confusing. We don't understand them. Everything, lots of things we don't understand. But if we systematically go in and select key observations and eliminate other ones and emphasize those that are most compelling, we can start to get at the real meanings of things. But of course, the story doesn't end there, because once we have that understanding, other questions start to emerge, and we have the opportunity then to propose new questions. And that's often the way that science advances, and in Georgia's case, the way her art was able to advance. So I will stop there and be happy to answer any questions. I see there are a number of them, but thank again the ACS for this opportunity to tell you about our research and ACS Applied Energy Materials.